Yeah, I hope you can see.
Yes, sir.
Welcome to the 11th class of CH uh, 10, not 10576. Okay. Now, in the last class, you're dealing with vibrational partition function, isn't it? So, I think we stopped somewhere here. You you know what is the vibration partition function? We have calculated this. This is the expression when the temperature is high. And this is a general expression for the vibration partition function, assuming that your uh, system is harmonic oscillator, simple harmonic oscillator. Okay. And then if you take log of this and take a derivative of that with respect to beta, multiply it with minus n, you get the thermodynamic internal energy. And this is the expression. Whereas theta v is called vibrational temperature, which is given by this expression, h nu by kb. Okay, so you can see that depending on nu, the value of theta v is decided. So nu is a molecular property, it depends on which molecule you're looking at. Every molecule would have a different nu vibrational frequency. As a result, it will have different vibrational temperature. So a temperature which appears hot or high for one molecule, it may not be high for the other molecule, depending on the molecule, of course. Yeah. So if you have a high, very low frequency, then theta v is very low, which basically means theta v by t is very low, isn't it? So theta v is much less than t in that case. Frequency is high, then theta v is high, like this. Anyways, so we have this expression. This ev is nkb times theta b by 2 plus theta v divided by exponential of theta v by t minus 1. So we'll start from here today. So what I have here is the expression for EV, and if I write it down, this is okay. This is the expression. Now, how do I calculate? For example, I can calculate what is known as vibrational contribution to the heat capacity. So this is something like CV vibration. And what is the definition of this? You know that you have to take a derivative of this EV with respect to temperature at constant n, isn't it? Of course, constant V. This is how it is. I hope this is fine with you.
Yes, sir.
And I know that, let me again repeat, because people are saying they're having problem with math. So you know the formula. This one is this is the formula. So now I use this. So if I take a derivative of this EV with respect to temperature, keeping these constants, so I'm going to get nkb the constant. Okay, this is the first time is nkb times. Now theta v is independent of temperature. No, this will be 0, the first term. What will the next term? nkb times, you know that what you're going to get, this whole square. The first term is theta v, which is 0, minus differentiation of this with respect to temperature, isn't it? So it will be something like exponential of theta v by t into minus 1 over t square minus 0. Is this clear what I have written here? I hope this is clear.
Minus
Sir,
theta v by
there would be
square.
theta p also.
Yeah, theta v is there. Sorry. So this is clear what I've written here. So this is going to be n kb. This minus minus will become plus. Okay. So I can say this is like theta v by t whole square exponential of theta v by t exponential of theta v by t minus 1 whole square. And this is your CV. Now just by looking whatever the expression is, but physically if I take a limit that your temperature is very high, what should be the answer? This is heat capacity. Any idea?
NKB.
Why nkb?
From equipartition.
Yes.
It's 2 degrees of no.
How many degrees? So this is actually for a you have vibration in one direction, no, one diatomic molecule, isn't it?
Yes.
N number of diatomic molecules. This is your collection. So each diatomic molecule has one mode of vibration, and each mode of vibration will contribute kVt, isn't it?
Yes. Yes.
Yeah. So if you have n number of such vibrations, because for each molecule one vibration, so it has to be n kVt. This is what is known as the equipartition theorem, isn't it?
Yes,
But this is only realized at high temperature, because equipartition theorem is classical, and the world becomes classical when the temperature is high. Okay. So I would expect the CV value should be equal to n kb, isn't it? Then what is EV? What should be the EV? EV or
NKBT.
EVI, whatever.
NKBT.
It should be nkVt. This is when temperature goes to, temperature is very large actually. Don't put this infinity, but it's very large. Okay. So can anyone how can you show this from this expression? Do you see
Sir,
that?
expand e per x expansion, series expansion of that.
Yeah. So let us do that. You have nkv. These are checks. You understand, no? Telling all of you that your calculation is correct. This is one check. So the I can write like this, no? Because I'm in the limit when t is very large.
So E won't be there, I guess.
Yes, less than 1. Okay. So t is very large. You understand what I'm saying?
Yes, sir.
When t is very large, you can expand the exponential term as this. You have say higher order terms. I'm not writing. What is there in the numerator? Numerator will have something like this one. I'm expanding actually. I want to expand. This will give me 1 plus other terms. Again, these other terms are even smaller. So what I can see here, it is now this is also small. You can neglect actually in the numerator. So what are you going to get? This one cancel, and this will come out. So you are going to get plus 1 plus this, but you can just again you have 1 plus this, but you just say this is 0. So what is the answer then?
So you have a square, no? T by theta v square.
Yes. Sorry. What is the answer then?
NKB into
NKB.
unity.
nkv into
Unity.
What?
But where is the temperature T?
It is CV, so why temperature would be?
Will it be CV? Will have temperature? No temperature.
No.
Yes, it is CV. Okay. So this is CV. This is fine. So I have checked this. Sorry. What about EV? Let us do it here. This is going to be what will happen to this? Now again this part is going to be 1 plus, isn't it? This one will give me NKV theta V by 2 plus theta V square by theta V, not theta V square, theta V, sorry, theta V by theta V into T, isn't it? This is how it is.
Yes, sir.
If I am doing wrong, please tell me. I don't think other terms are not writing.
Yes, sir. This is correct.
Yeah, so this is going to be equal to NKVT because again you are in the limit when your temperature is much greater than your theta V. So this term you can neglect. So yeah, this is also checked. Okay, so you have general temperature expression. Also you have expression for other temperature. So now if I plot this, we do it here only. If I plot this CV as a function of temperature, what is going to happen? It will start from 0, no? It should start from 0 and it will increase and then it will saturate. What is the saturation value?
NKB.
It's NKV. Sorry. This value. Okay.
Yes, sir.
This should be the way. Actually, you can go and check. You can do it on a computer and see how it is, how good it is. So I can also calculate, for example, fraction of molecules in the excited vibration state. How do I calculate?
This
In state n. Then what will be the answer? This is something like fraction, no? This is f of n, I can call it. And this expression, you know, this is essentially exponential of minus beta.
n plus half.
Yeah, so it is h nu n plus half, and I have to divide this by something. What is that?
Partition function.
This is a partition function. It is a function of temperature, of course. This is for the nth level, nth vibrational state, isn't it?
Yes, sir.
And if I plot this, for example, what do I expect? If I plot this as a function of n,
Falls very rapidly.
yeah, so because the maximum population would be n0, no? And then it should decay, isn't it? You will see that most molecules are in the ground vibrational state at finite temperature, unless the temperature is very low, isn't it?
Yes, sir.
Hello, sir.
Yes.
Sir, here S nu n plus half is the energy of the level, nth level.
Yes, nth level. I'm calling about this nth state. What is the fraction in nth state?
Okay, so
Nth
that is
level.
understood.
Yes.
Good.
Yeah. It's fine. The most molecules are in the ground vibrational state. But actually, I can always define for a general thing, like I have n plus 1, n plus 2, n plus 3, like this, isn't it? Like 1, 2, 3, 4, like 0, and then I have higher levels. So I can just take any level which is above 0. So I can define this fraction, which basically means in total number of population in the higher excited states, the fraction of population. Okay, fraction of molecules in the
Yes,
all
sir.
excited states collecting. So this will be what? This will be, you have to take a sum of this, no, this quantity. And the sum will be from n from what to what? Tell me. Should be 1
1
to
to infinity.
infinity. And can you just simplify this? What is going to happen to this term?
Matrix series.
Yeah, can
Yeah.
you tell me? Can you tell me what is the answer? Can you simplify this?
Yes, sir.
What will be the simplification? Tell me. Any suggestion? How to simplify this?
You can take e power minus beta h nu by 2 outside.
Okay.
Then that is sum over n.
Also, I can take this, no, this outside.
Yes.
And this you have
Beta and h nu.
n. But you have n1 starting from n1,
Yes.
isn't it? So actually, I can write like this. This one I can write it as now I can write 1 plus this. So let me write it. Better to write like this. I just take this like this. 1 plus this minus 1. Can I write like this? Just a manipulation, no?
Yes, sir.
So what is this? Now you know the answer.
Partition function.
Because if I go like this is going to be, you know what is going to be answer. 1 plus x squared like this, isn't it? Isn't it?
Yes, sir.
So you are going to get 1 by yeah, you can just take this
1 minus
1 minus beta
beta.
h minus 1, isn't it?
Yes, sir.
And what is good this? If I have not done anything wrong, I think this is fine, should be fine. This is how it is, no? This is how, so this is what this is? Q vibrational. This is Q vibrational, isn't it? So if I multiply this is Q vibrational, so they will cancel. This will give you 1 minus by. Is this correct? What I have done? I hope I have not done anything wrong.
Yes, sir.
Yes.
If
Yes.
n greater than 0 has
Yeah.
to be 1 minus
Yeah.
f0.
And what is this? This is nothing but f0, isn't it?
Yes, sir.
Because your f0 would be something like and then can I simplify further? Yes, I can simplify further, isn't it? What is this? 1 minus f0. 1 minus f0 is what? Because if I put the expression of this vibrational partition function, this is vibrational partition function, isn't it?
I think that denominator.
Just a minute. I can keep it like this, but I am saying that 1 minus f0. Let me do it here again. So what is 1 minus f0? 1 minus f0 has to be equal to 1 minus e to the power of minus beta h nu by 2 divided by, this one is e to the power minus beta h nu divided by 1 e to the power minus beta h nu, no? By 2, no? This one? This is how it is. Isn't it? If I am,
Yes.
so this is going to be, this will cancel. It's going to be, isn't it? This is going to be like this. So what is the answer?
E power minus beta h nu.
What is this? This is fine.
Yes, sir.
So your f n greater than 0 is given by this. But what does it tell you? Take it, see it carefully. What does it tell you? So I give you a temperature. Temperature is constant, 300 Kelvin, any temperature. So this fraction will decay faster if theta v is large, isn't it?
Yes, sir.
So some theta v is equal to, what is the theta value expression for theta v? What is the expression for theta v? Tell me.
H nu by kb.
H nu by kb. Now kb and h, they are constant, no? So it is molecular property is this. This is molecular property, no? Frequency.
Yes.
Frequency. So basically it depends on which molecule you are looking at. If I give you the value of your theta v for the molecule, then you can tell me which will decay faster, isn't it?
Yes, sir.
So I'll give you some value of theta v for some molecule. For example, this, if I put theta v and the molecule, if I take oxygen, say I have some data for some, I should also have some data for diatomic molecule. I think it is better to give data for diatomic than polyatomic, because this will give you an idea about the value of theta v. Okay. Yes. So for example, if you take hydrogen molecule, the theta v value at 300 Kelvin, okay, no, that is not temperature, but your theta key value is 6215. Okay, in Kelvin. For HCl, it is 4227. Okay. For iodine, what do you expect? Iodine, I can tell you, this is 310. For chlorine, what do you expect? Lower or higher?
Higher than iodine.
So chlorine is 108 and 810. So these are the values of theta v. Okay. So depending on the theta v, for example, if I have a theta v which is large, for example, for one molecule, then this decay will be faster. This f of this fraction will decay faster, isn't it? What does it mean, Anish, or anyone other than Anish can answer also? What does it mean? If your theta v is large, it decays faster. What does it mean? What does it mean?
Lower will be the fraction of molecules in excited state.
Lower will be the fraction of molecules in the excited state. So if I give you hydrogen and iodine, which will have lower population in the excited state?
Hydrogen.
Hydrogen. So because the energy gap is larger in hydrogen than iodine. Is this clear?
Yes, sir.
It comes from quantum mechanics, isn't it?
Yes.
So just a small connection with quantum mechanics. So now after doing vibration, now let us move to rotation, which I promised in the last class that we'll do rotation. And we'll do rotation for the heteronuclear diatomic fast. Okay, now some students are there today. So I just ask, how many of you have taken CH408?
Yes, sir.
This is Kailash. Who else?
Yes, sir.
Who is this?
Ajit.
Okay.
Yes, sir.
So how many are there who have taken?
I think, sir, all MSc guys.
Yeah, how many are there? 5, 6 are there, maybe, I don't know. Maybe 5.
Yeah, more than 5,
Yes,
I
sir.
think.
Anyway, so you must have learned all these things, isn't it? So I'll ask question, you answer, huh? Is this fine?
Yes, sir.
Okay. So let us write down the rotational partition function. What is the expression? What is the expression?
Summation over
2j
GI.
plus 1.
Yeah, you know this is the quantum number is j, goes from 0 to infinity, but you don't forget the degeneracy, which is 2j plus
2j
1
plus 1.
minus
Then
beta
energy
J-
Hc
Epsilon J.
j into j plus 1
Yeah.
into b bar. We have done in the last class the notations.
Hello, sir.
Yeah,
Sir, do I need to remember these things like degeneracy number and
yes, you have to remember 2j plus 1. If you cannot remember,
no,
you
only
can
for this system, like others, like
yeah, of course.
can there be different systems in the questions?
Yeah.
Because I've not taken quantum.
No. 2j plus 1 you remember, yes. 2j plus 1 you remember. Okay, this is very standard in rotation. Okay, now if I take b bar divided by kb, I can define something like another temperature. This will be like rotational temperature or characteristic temperature of rotation. Okay. Now, usually, is this theta v by t is quite small at ordinary temperatures, like room temperatures, around room temperature. Someone's mic is on. Some noise is coming. So what do you do? Of course, then the above sum can be replaced by an integral, isn't it?
It should be theta r by t.
Yeah. So above sum can be replaced by an integral, isn't it?
Yes, sir.
So then what is the expression? This expression is going to be how do you do this integration?
This
Yes,
is
sir.
actually differentiation of exponential j square plus j. We'll have to recognize that.
Yeah, exactly.
So this is beta theta. So I can just write it little slightly better. Isn't it? This is how it is. So now let us take, I call this y. Okay, so this gives you 2j plus 1 . This is what you get, na? Integration limit does not change. This is dy, but what is 2j plus 1? It is t by theta r times dy, isn't it?
Yes, sir.
Yes, sir.
Isn't it? This is how it is. 2j plus 1 dj is the dy times theta r by t, and this one is and if I integrate this, what I'm going to get? I'm doing all the steps. What is the answer?
Unity. I think.
Okay, this is going to be minus 0 plus 1. So this expression is valid when?
When
When the
temperature is high enough
yeah,
for
when the temperature is high. So basically your temperature has to be very high. Temperature has to be very high. So it basically means this is high temperature limit, no? Okay, this is high temperature limit.
Yes, sir.
So when you do this calculation at high temperature, then you are all set. But if you don't do it at high temperature, then you cannot do this. For example, for low temperature, for example, or with molecules with high value of theta, such as for example HD has theta r, which is 42.7 Kelvin, quite large. In that case, one cannot use this expression. Integration to evaluate the partition function. Then you have to take the sum. You know, it is 2j plus 1 into this, all the sum. And if you do carefully, it is very lengthy. I'm not going to do it. You can do yourself. And in order to do that, you have to use something. I'll tell you what is that. If you do this, you'll see that you're going to get something like this. And I have used something here. This has a name. I think some of you will know that actually for sure. A BTech student, they must have heard this somewhere. This is called Euler-Maclaurin summation formula. It is there in the book by Euler-Maclaurin summation formula. Sorry. In the book by Donald McCurry. You can have a look there and you will see this is the expression you get. This is for ordinary temperature or not so high temperature. Okay. This is when your theta r by t is large. Okay, it's clear.
Yes, sir.
So if you are very much interested, you can go and check how to get it. But in most of the cases, we are good with this high temperature expression. Okay, we will take high temperature expression for theta r by t less than 1. I know what will be the E rotation. You know, it is n d ln q rho t divided by dt
PB.
into kbt square, isn't it?
Yes, sir.
What will the answer? N kbt square. And you know that it is, what is the t by theta, no? The expression is t by theta r. So you have to take a log of that, no? So essentially what you're going to know to ddt of ln, sorry, so many mistakes. What is the answer?
N kbt.
You know that it is because the theta r will be 0. You can expand this. I mean, you can just write ln t minus ln theta r. So only the first term will contribute, and it will give you. And this is what you expect, isn't it? Again, equipartition.
Yes, sir.
Equipartition as according to equipartition theorem. So
Hello, sir.
yes, what will be the CV? Yeah, let me write down the CV and then you ask. You know what is CV? CV for rote. It has to be NKB. Yes. Tell me, yeah. Someone has a question.
Sir, suppose if we are so this E value, this is the thermodynamic internal energy when we use the rotational part. So if we use the others like Q trans and all, will we also get the similar type of expression? If we also include Q trans and Q vibrational.
See, what happens, the equipartition theorem tells you that for each degree of freedom, you have half kVt. You know that.
Yes, sir.
For translation, you have only 3 direction, x, y, z direction. Each direction, half kVt, half kVt, half kVt. So you will get 3 by 2 kVt. This is done in the last class, maybe, no?
But both are like internal energies. Both are thermodynamic internal.
Yes. So this is the contribution. This is a part of internal energy due to rotation. Or the contribution from rotation. This part.
Okay, sir. Thank you.
So your total internal energy will be a sum of all this, no? Because your partition function is a product of all the partition function. So
Yes.
your rotation energy will be internal energy of entropy. All will be sum of all this, isn't it?
Yes, sir.
So I'm
Thank
doing
you,
this rotational part. So now let us go back and I can also do this known as nj by n. What will be the answer? Nj by n. You know, this is just like for the jth level, so it has to be. This is fine, no? I'm writing like this.
Yes, sir.
Divided by clear? Is this clear?
Yes, sir.
So now, if I plot this, how does it going to look like? A plot of this. Versus J. So if you don't have 2j plus on, it will decay exponentially, isn't it? Not exponentially, but exponentially of minus j square kind of thing. Anyway.
Yes, sir.
So it is not going to decay exponentially, but yes, but you have a quadratic, which is which is of course, but if your j is positive, then it will decay. You have only the decay part, isn't it? And j is 0 to infinity. But you have 2j plus 1, so this will compensate because there is a competition between these two terms, 2j plus 1 and this exponential of minus j square kind of thing. Okay, is this clear? So if I
Yes, sir.
plot this, I think it is done in spectroscopy course in physical chemistry, I'm sure. If I do this, of course, I start from J0. Even J0, what will be the value? Nj by n? Some
1
value.
by
Some value, no?
1 by partition.
If it is
Yes.
J0, some value, yeah, something. Will start from here and then they'll increase. Increase is because of this, and then it will decrease. And eventually asymptotically go to 0. But there will be a value of j, which we call j max, for which this ratio is maximum. What is j max? How to calculate?
Differentiation.
How do you calculate? Yeah, you're
Differentiate
saying
with
something.
respect to-
Yeah, so can anyone calculate? It's not very difficult, no?
So this is maxima minima problem, so we can differentiate and then equal to it 0.
Yeah. So basically ddj of whatever nj by n whatever. Actually nj by n has to be 0. So this will give you 1 by q rotation is a constant. It has with j. Basically you have to take a del j of this quantity.
Sir, Q rot also has J corporate, I guess. So why it would be constant?
Why q root has j? Tell me.
So it is the partition function.
No,
So it
no.
is summation.
You have already sum over j. You already summed over j. Why would it depend on j? It's a constant. It depends only on temperature. We have just done this, no? We have just done this.
Yes.
So any partition function, vibration, it doesn't depend on vibrational control number. No. The expression depends on vibrational control number, but when you evaluate, after evaluation, it does not depend on that quantum number, isn't it? You have summed over all the quantum numbers.
Yes, sir. Yes.
Yes. So if I do this, this has to be 0. So I just concentrate on this part. This part will give you it's a product of two function. It is going to be 2 into 1 plus 0 into the power of theta r into j plus 1 by t plus what is the next term? Tell me. Someone tells me.
Minus theta r by
Yeah,
t.
because you have to, and this one minus theta r by t into 2j
J
plus 1, isn't it? And the whole thing has to be 0.
0.
I can take this one and this one, you can just do, isn't it? So you are
Yes,
going to
sir.
get 2 plus 2 into 2j plus 1 minus theta r by t is equal to 0. So this will give you,
2j plus 1 square.
yes, sorry, 2j plus 1 square is equal to theta r by t. Did I do anything wrong?
There should
I
not
think
be a
2 is not there, I think.
Yes.
2 is not there because this 2 is not there, isn't it?
Yes.
This one is not there. So what I have here is
So it is 2t by
uh,
theta r.
2j plus, yes. I'll just take this. Yeah, that gives me some trouble sometimes. This is what it is, no? Or 2j plus 1 is or J is, which actually I'm calling J max, because I can call it here, but I am just calling it here. It is obvious that is going to be this is the answer, no? I can rearrange it a little bit.
Yes, sir.
It is going to be T by so which is equal to T by 2 theta r, you know what is the value definition of theta r? Theta r is
D bar by KP.
yes minus half, which is equal to, I can write it like this, of course half, because I just neglect the half, because you will see that this quantity is much bigger than half. Okay, so this is just to show that there will J max value for which this population is maximum. This was done in spectroscopy courses, isn't it? Kailash, Deepak?
Yes, sir.
Yes, sir.
Yes, sir. Right.
So they would not do the derivation, maybe, I don't know, but they would say this is how it is. Okay, this is done. Now, up to this is fine, but when you go to homonuclear diatomic molecule, your things become quite difficult. Not difficult, it's quite involved. Any idea what will be the expression for homonuclear diatomic, or why it is different from heteronuclear diatomic?
So due to exchange,
A
there
2
should be
comes
some
in the
need.
denominator.
This is done, no? This is done in
It
your
was done.
Symmetry.
It was done, but not derived.
The symmetry number, I think.
okay. Okay, it was not derived. We'll try to see what happens. Okay. Now, homonuclear diatomic molecule means could be hydrogen. Now, in quantum mechanics, you know, this total wave function, I can write as a product of what? For a diatomic, you know, that you have translational partition, wave function times, say, rotation times vibration times electronic, what else? But you see that you also have nuclear partition function, isn't it? You have the nucleus, the spin of the nucleus itself. You can add this. Okay, is this clear?
Yes, sir.
Now this hydrogen, we'll see what is there. So we'll do two operations. Okay, let us do a two-step operation. So what is the step one? Let me write it down. So an inversion of all the particles, electrons and nuclei through the origin. You have to think little bit classically, but you're dealing with electrons and nucleus. Okay, then what? Then you do an inversion of just electrons back through the origin sorry for this handwriting because I have problem writing here, and this two-step process is equivalent to an exchange of nuclei.
Inversion means inversion of coordinates, positions.
Yes, I'll tell you. Yes, coordinates. Yes. Okay. Now let us see what happens when I deal with translational wave function, translational motion. What do you expect? What do you expect when you do this operation? See, translational motion means the motion of the whole molecule, isn't it?
Yes, sir.
The motion of center of mass of the molecule. So that has nothing to do with inversion. So not affected by inversion. Okay. So translational is not a problem at all. It is not affected by inversion. What about electronic wave function? Can anyone tell me? What do you expect?
Antisymmetric.
Antisymmetric or symmetric, you don't know. How do you know it is antisymmetric?
So based on the nuclear spin or
No,
spin
no,
of
no,
the
no nuclear spin. I'm talking about electronic wave function.
oh,
That depends on the symmetry of that electronic state actually. Sorry. So it depends on the symmetry of that electronic state. And what is the symmetry of the electronic state?
Antisymmetric as per
No,
Pauli.
no. Don't. It is a molecule I'm dealing with. It's a molecule, H2 molecule. Now, I assume that H2 molecule is in the ground electronic state. This is given by, I know whether you know this. This is sigma G plus terms and symbol. If you know terms and symbol, huh?
Yes, sir.
sir, yes,
Yes.
sir.
Remember
Yes, sir.
Yeah.
term symbol?
Yes, sir. Remember.
So basically, if it is sigma G plus, it is symmetric.
Symmetric.
Electronic. So translational does not get affected. Electronic, I assume things are in the ground electronic state. So I know the electronic wave function is symmetric. Okay, ground electronic state. Okay.
Yes, sir.
Sir, sir, one question.
Yes.
Sir, there is a statement. This two-step process is equivalent to exchange of nuclei. So, sir, why we are only taking the exchange of nuclei, not the electron in a in this case?
No. Yeah. What I'm saying that, see, the point is as follows. I want to see what is the symmetry of the molecule, diatomic molecule. Okay. And I'm going to deal with rotation and nuclear partition function. Okay. Rotation and nuclear partition functions. We'll consider nucleus as well as rotation. Okay. So let us
Yes, sir.
consider only nucleus and rotation. It will be clearer as we
Okay,
progress.
sir. Okay.
As
Okay.
we progress, it will be clearer. So the psi total will be affected by, not affected by translation, but will be affected by electronic. Of course, if I assume this is ground state, then it will not be affected, isn't it? It is like symmetric. What about rotation, vibration, and nucleus? Can anyone tell me? Vibration, rotation, of course, the zeroth level approximation.
So nothing will be affected by this.
No, just think about it.
Uh,
Vibration also, you'll see that if you do this, psi vibration,
Do we assume ground state?
yes, I assume that potential is symmetric, or doesn't matter, but depends on essentially R minus RE. It is a deviation from the equilibrium geometry, isn't it? The magnitude of course, I assume it is symmetric. If it is, because I am assuming the harmonic oscillator, okay? Then again, it is unaffected, okay? So unaffected by any inversion operation.
Yeah, we are assuming it is in vibrational ground state.
Not really. I'm assuming that it is in a symmetric vibrational potential, like harmonic oscillator. So it is around R equilibrium, it is symmetric in both the directions. It depends on the magnitude of R minus RE, not the sign.
So that is true for like V. It is true, but if you take say first excited Hermite polynomial, then it is antisymmetric in X, right?
Yeah, if you call if you go to the higher vibrational level, you're talking about. Yes.
Yeah. Like all the odd order.
Yes, you can think, but you're saying that if you are in the V equal to 1 level, then your wave function is antisymmetric. But
Yes.
what is this operation? What is
Replacing
this
X building in X.
this operation, does it affect the vibration? Because I am not doing anything with the vibration, isn't it? I am not doing anything with the vibration. I will do operation when I go to say let us go to the rotation thing. Okay. So if I go to rotation, if I do the quantum mechanics of rotation, what I get is that if I do the rotation, I get rotational wave functions. If I do the quantum mechanics. And you solve rigid rotor problem.
PL of cos theta, if I'm not wrong.
Yes.
Legendre polynomial.
Yes. And then I get states. One state would be something like this, spherical. It is just like your angular part of your hydrogen atom problem, isn't it? But you are doing it for a rigid rotor diatomic molecule, okay? So I'll have J equal to 0, M equal to 0 state. This is like an s orbital, isn't it?
Yes, sir.
Like s orbital. So I can also have a situation like J is equal to 1, M is equal to 0. What will be this? This will be like PZ orbital, isn't it?
Yes, sir.
So I can also have other orbitals, isn't it? Like I can think of something like this. But remember, you remember that these are not orbitals. These are actually solution to your rigid rotor problem. Solution
Yes,
to
sir.
rigid rotor problem.
Contour plots.
Yeah, not contour plot, because it's contour plot you can think of. It's a contour plot. Sorry. Okay, so like this. So I can do plus, minus, whatever the way you want to do it. It's not important. But these are getting affected. These will get affected. These wave functions will get affected. by inversion. Because some of them are symmetric, some of them are antisymmetric. Okay, is this clear?
Yes, sir.
Because what will happen that if you do this inversion, your r theta phi, any point on r theta phi, after this thing, it will become like r pi minus theta and phi plus pi kind of thing. So your coordinates are going to change. It can be seen if you go to the expression. I'm not doing the quantum mechanics, or pictorially you can see that this is going to change. Okay. So there will be two class. One is J odd and one is J even. Okay, you know they are different, J odd and J even under this operation. Now after that I just look at nuclear part of the f function. If I look at the nuclear part of the wave function, what do you expect? You have done helium atom, no? All of you?
Yes,
All of
sir.
you have done helium atom.
Yeah.
It is like helium atom, but not
Yes.
helium atom. It is like, it is a hydrogen molecule. Isn't it? And each nucleus has a spin. Like this. This is a very bad way of saying, because spin is not a classical thing. But I'm just showing it like this. So how many spin wave functions are possible? You know that. That I can have a situation like alpha alpha, both are up, beta beta, alpha on of nucleus 1. This is a nuclear spin. Dealing with nuclear spin, not electron spin. Okay, is this clear?
Yes, sir.
Yes, sir.
Basically, I'm changing the nuclei. I'm not changing the electrons in that sense. So alpha alpha, beta beta. What else? I can have alpha beta plus
Beta
beta
alpha.
alpha. You have to multiply this with this, and these three are symmetric. You remember?
Symmetric.
But these are not like, it is not helium atom. It is not electronic spin. This is hydrogen molecule. We are talking about nuclear spin. Is this clear, Anish?
Yes, sir.
If you do NMR, I think you know this. And but I will also have this combination. This is antisymmetric. Okay,
Yes, sir.
is this clear? Is this clear? I think it should be clear. It's not a difficult
Yes.
thing to do. Okay, so this is a hydrogen molecule. So if I assume, if I have hydrogen molecule, for example, in the ground electronic state, I know this is this electronic state I'm talking about. So the symmetry of the total wave function will be determined by nuclear and the rotational wave function. Is this clear?
Yes, sir.
Nuclear and the rotational wave function. But in general, if I is the nuclear, like I, you know that nuclear spin essentially. It is like S. So each nucleus has how many spin states? Each nuclei.
2i plus 1.
You know this, no? This is like helium atom, you have 2s plus 1, like here. States. spin states, of course. These are nuclear spin. And how in diatomic, how many nuclei are there?
2 nuclei.
One nuclei. This one has twice I plus 1 state. This one has twice I plus 1 spin states. So total number of spin states, how many?
Pair of.
It has to be for the diatomic, isn't it?
Yes, sir.
And some of the spin state would be symmetric and some of them would be anti-symmetric, isn't it?
Antisymmetric.
And actually you will see that you can show that it is twice I plus 1 into twice I by 2. This is the number of antisymmetric spin states. Okay, antisymmetric spin states mean that if I have in general, it is like this: alpha I 1, alpha j 2 minus alpha j 1, alpha I 2, isn't it? Or yeah, one thing, alpha I 2, alpha j 1, if you write like this, 1 by root over 2. This is the general statement, no? Is this clear?
Yes, sir.
So how many number of symmetric spin state, how many are possible? It should be twice I plus 1 whole square minus what is the answer?
I plus 1 into 2I plus 1.
This is the answer. Okay, the number of symmetric spin states. Now let us check this. For H2 molecule, what is the value of I? I is half. Okay, then number of antisymmetric spin state are how many? What is 2 by 2, 1, matching?
Yes, sir.
And number of anti-symmetric spin states? What is the answer? Is 1 plus 1 2, 2 into 1.5, which is 3.
3.
So you know this, no? These 3 I have just written here. These are 3 and this is 1. This is for general. So now I have a rule. Then you have a system. If the molecule is such that there's a gap. Okay. If the molecule has integral spin, the molecule itself, then the molecule is called what? You know, these are called boson.
Boson.
Okay. And if the molecule has half integral spin, it's called
Fermions.
fermions. So if I have integral spin, then the total wave function has to be what?
Symmetric.
Symmetric.
How can you make them symmetric? Make it symmetric. So you have, if you have I into twice I plus 1, antisymmetric spin functions, spin wave functions, nuclear, I should say nuclear spin functions, it will combine with what? Because antisymmetric should combine with another antisymmetric to make it symmetric, isn't it?
Yes, sir.
To J odd. Is this clear?
Yes, sir.
What about other possibility? Other possibility is that I take this I plus 1 into twice I plus 1 symmetric nuclear spin functions or spin wave functions, and they will combine with or couple with
J even.
J even, because this is symmetric, this is symmetric, the total is symmetric. Now what will be the rule for this? Antisymmetric nuclear spin functions, it will combine with what? Because the whole total wave function has to be
J even.
antisymmetric. So it has to J even, and then this I plus 1 into twice I plus 1 symmetric, that will combine with, and this is a case example is H2 molecule, isn't it? This is an example. H2 molecule has to be an example. Is this clear?
Yes, sir.
So I can write down the expression now for the rotational partition function. So my rotational nuclear partition function. Now I can tell me what is this. So I just write down for half integral spin. If I write down for half integral spin, I can write it for here also. Let me write down for the integral spin first. Q rot nuclear function of temperature. Can anyone tell me what is this going to be? Because I know I plus 1 in twice I plus 1, no? That should be multiplied with J. Tell me. J even.
1.
J even, not 1. J even into 2J plus 1 exponential of minus J into J plus 1 theta r by T. Is this clear? This part.
Yes, sir.
Plus, I will have what? Plus
I into
I
2I
into
plus
I
1.
J odd. I am not writing. You understand? Here, what is going to happen? J
Odd.
and then I have this expression not writing. Is this clear?
Yes, sir.
So actually you cannot, even in this case you cannot write that Q rot Q nucleus is not actually product of this for homonuclear diatomy. Can you see this? Can you see this?
Yes, sir.
So now let us go back. At ordinary temperatures, most of the times your theta r is small. Then what can I do? I can just all the sum, I can write it as integral,
Yes, sir.
isn't it? half, of course. J even equal to J odd, that should be half of the whole integral, isn't it?
Yes, sir.
Okay, what is the answer to this? You know this. This is half into T by theta. We have done this, no?
Yes, sir.
So now let us go back and check for integral spin. For integral spin, what will be the answer? You know, integral spin means I plus 1 into twice I plus 1, no? Into half T by theta r plus I into twice I plus 1 into half T by theta r. This clear? Just say go back to this expression. This expression I'm using. This one
Yes.
is, you know, half. I'm just putting it there. Now, if I simplify this, what I'm going to get? Okay, let me take this. If I take this common, what I'm going to get? So what is the answer? Is this clear? What I'm written?
Yes, sir.
So Q wrote nuclear. And then it's taking so much of time. This part I can call it maybe Q nucleus, and this I can call it Q rotation. Only high temperature limit. Okay. For half integral spin,
The same expression
yeah,
should
yeah.
come.
Sometimes I don't know what is the problem. Sometimes it, but you have to remember that this is only when your temperature is high. Is this clear? If your temperature is not high, you're not going to get it. Because you cannot really write this as integral. Is this clear?
Yes, sir.
That is very important. That you cannot write it as an integral. So other than Anish, others are following, I hope. Because he is the one who is saying yes, sir, yes, sir. Anyway. So Q wrote nucleus at temperature T. If I do the same thing for the other case, I'm going to get the same expression. Okay. So I can see that your theta of rho, sorry, not theta, Q of rho. I can write like this. Now I can say this is your Q of rotation. But what is, it is different from your heteronuclear diatomic, isn't it? How it is different?
Half
2,
factor.
1 by 2.
You can see the factor of 2 there, 1 by 2. So this 2 is called symmetry factor. I think you have been introduced to this, isn't it? The symmetry factor, the symmetry
Yes.
number.
Yes, sir. Yes, sir.
This is how it is done, no?
Yeah.
This is a symmetry number.
Hello, sir.
Yes.
Sir, can this be compared to that indistinguishable and distinguishable particle, the n factorial divided by n factorial when it is indistinguishable.
No, it is not like that. It is not like that. It is not like this. For the rotation, no. It is in a way it is, but it is not like that. It is not like that. Symmetry number is different.
Sure.
This is different. When you do polyatomic molecule, you'll see. If I get a chance to do polyatomic molecule, we'll see that it is different. Sometimes I have problem in this because I think it is too heavy. I am writing so many things, no. Your because even if I open this, disconnect this, then also I think I have this problem. There's a problem with the PowerPoint. So what I can do, I can just want to take 5 more minutes because I don't think I can finish what I was planning. So I'm saying that, okay, your Q rotation homonuclear diatomic, huh? Is half. This is called the symmetry number. Okay, this was a symmetry number. And I think I'll stop today because now in the next class I'll go from here. I want to discuss what is known as ortho-para hydrogen. Was it done, ortho-para hydrogen? Because I could not do today because of this. You can try doing. But it doesn't look like I'll be able to do this today. Okay, so ortho-para hydrogen is like, you see that I have like 2 things in hydrogen molecule, isn't it? In one case, I think my spin states are antisymmetric and my J are symmetric. J are even. Okay. In another combination, it is the other way. In another combination, is the other way. Your spins are symmetric. Spin part is symmetric, and the J is odd. Kailash, are you there?
Yes, sir.
So actually, I'll have what is known as like depending on the spins on the nucleus, whether they are parallel to each other or they are antiparallel to each other. I can have situation like parallel antiparallel is not the right word to use. Rather, I'll say whether the spin wave function is symmetric or antisymmetric, depending on I'll define what is known as ortho and para hydrogen. What is ortho hydrogen? Ortho hydrogen is when the spins are parallel in the sense that nuclear partition function, the spin part of the nuclear spin partition function, wave function is symmetric. On the other hand, for ortho, what will happen? For ortho, this is ortho, but what will happen for para?
Paired.
Para, it will be just opposite, isn't it? Okay. So I can actually briefly I can tell you, because I have some time. Briefly I can tell you that if you do this for H2, your Q rot nucleus, it is going to be, if you go back and see that J even would have 2J plus 1 exponential of minus of, okay, the way it is written, okay, J into J plus 1 theta r by T plus 3 times J odd. Okay, is this clear?
Yes, sir.
So this is coming from which part? The J is odd, total has to be odd. Then this 3 is coming from antisymmetric. Antisymmetric means what? They are kind of paired, loosely calling, isn't it? This is what? This is para.
Symmetric.
This is para. Or it is ortho. It is actually ortho. Because 3 is, sorry, 3 is actually symmetric. So actually this is ortho. And what about this guy? This part? This is para. It's ortho. So I can always calculate at any temperature, given temperature, n ortho by n para. This is going to be given by 3 times this j odd. I'm not writing again. 1 times j even. So j even. And what will be this value as my temperature increases?
Approaching 3.
This will be 3 as T increases. High temperature is T. So 75% ortho, 25% para. So if I actually, people have shown that percentage of para H2 as a function of temperature, what do you expect? The temperature is very low, it is all para. Okay, then it drops, and eventually in the high temperature limit it becomes 25%.
Is there any experimental method to distinguish ortho and para?
There should be. There should be. And the best thing is to see their rotational spectra. Their rotational spectra is different, isn't it? Because in
Yes, sir,
ortho, the population is only odd levels, odd J levels. And for para, it is only even J levels. It should have been taught in spectroscopy course. Should be. I don't know it's taught.
Sir,
But actually, you can calculate heat capacity divided by n kV. Let me finish this and they'll answer. Okay, if you do this, you will see that, okay, experimental value will be like this. These are experiment. Okay, these are experimentally measured. And if you calculate only for ortho, it will be something like this, ortho. Only for para, it is something like this. The equilibrium mixture means the mixture at any given temperature will be like this. Why it is happening? Because at any temperature, if the temperature is low rather, or any temperature, the conversion between ortho and para is negligibly small. So in experiment, you cool the system, you have you prepare. So what you do actually in experiment, let me tell you. Maybe you have class, somebody has a class, you can leave. Just I'll take 2 more minutes. Actually, I'll suggest you to go and read the book by Mercury. Statistical Mechanics. So what happens that you go and read it. If you have any problem, you can come back and we can discuss in the next class. I think that's better. Okay, because I'll stop here. Otherwise, I think I need some more time. Okay, so I think it is enough for today. Now somebody has a question.
Sir,
You can ask
rotational
it.
partition function.
Yes.
Sir, rotational
Yes.
partition function will be divided by 4 for
4. Why 4?
Yes, sir. Hello.
Yes, tell me.
Sir,
Why 4?
partition function with sir whether partition. Sir, sorry, I'm not clear.
No. So the
Sir,
rotational
I'm
partition.
asking whether the rotation, Q rotation.
Q rotation is divided. This is the Q rotation, homonuclear diatomic. T by theta times half. This is the expression. This is a partition function, rotational partition function. We have just done this, isn't it?
Okay, sir. Okay, sir. Okay.
Sir,
Yeah. What is the question? Actually, did not understand. Yes, tell me. Tell me, Kailash.
Sir, can you increase the assignment submission date to Sunday?
Why?
In Saturday, Sunday, we will be able to solve all the questions.
Okay, Sunday. But Sunday you have to submit by Sunday night. Okay, is it
Some
clear? Okay, Sunday.
Saturday.
Take time. Yes, take time.